Hello everyone! In this lesson, we will continue to study the frequency domain analysis module of continuous system. In the previous lecture, we introduced the concept of ideal low-pass filter. Today, let's discuss its characteristic. The main contents include the frequency characteristic of ideal low-pass filter, impulse response of ideal low-pass filter, step response of ideal low-pass filter, rectangular impulse response of ideal low-pass filter, and finally, I will introduce an achievable low-pass filter. First, let's take a look at the frequency characteristic of an ideal low-pass filter. This is its frequency domain waveform. Figure A shows the amplitude frequency characteristic. Figure B shows the phase frequency characteristic. The mathematical model of an ideal low-pass filter has three forms, including Formula 1, Formula 2, and Formula 3. Generally, when solving the impulse response Ht of an ideal low-pass filter, we can use Formula 1. From its frequency domain waveform and its mathematical description, we can find that the cutoff frequency of the ideal low-pass filter is omega c. It is called the passband of the ideal low-pass filter. Obviously, the signal in the low-frequency band from 0 to omega c can be transmitted without distortion. Let's analyze the response of the ideal low-pass filter to the impulse signal. Let's look at its mathematical model. If the system function of the ideal low-pass filter is Hj omega, we need to take the inverse Fourier transform of Hj omega. According to the definition of Fourier transform, Ht should satisfy the formula 4. Because the spectral characteristic of the ideal low-pass filter only appears between minus omega c and omega c, so we can turn formula 4 to formula 5. Here you can find that this is the integral of the exponential function. We should use the property of the integral of the exponential function. Then bring its upper limit and lower limit into the expression. We can get the mathematical description of Ht as shown in Formula 6. Since Formula 6 conforms to the characteristic of sampling function, so equation 6 can be turned to equation 7. This is the time domain mathematical model of ideal low-pass filter. Let's take a look at specific waveform of the impulse response of the ideal low-pass filter. This is its input signal delta t. This is its output signal Ht. Formula 7 shows its mathematical description. Here we can find that the output and the input of the ideal low-pass filter produce significant distortion. Let's make a further analysis of its performance. By comparing its input signal and output signal, we can find that there is distortion between them. Well, what is the cause of distortion? We know that the bandwidth of delta t is infinite. The passband of the ideal low-pass filter is from 0 to omega c. When delta t enters the ideal low-pass filter, the frequency components above omega c are filtered out. So its spectrum is distorted, and its time domain signal will also be distorted. If we gradually increase omega c to infinity, at this time Ht can approach delta t. In this way, the system becomes an all-pass network. It can achieve completely distortionless transmission. From the time domain characteristic of the ideal low-pass filter, we can find that it is a non-causal system. Therefore, the ideal low-pass filter is not a real system in physics. Let's look at the step response of an ideal low-pass filter. First, let's look at its mathematical model. The input ft is a step signal. The spectral characteristic of this step signal is shown in Formula 8. The spectral characteristic of this system is shown in Formula 9. In time domain, the response of this system yt is equal to the convolution of epsilon t and ht. According to the time domain convolution theorem we learned before, obviously, its spectral characteristic conforms to Formula 9. In this way, the output yj omega of the ideal low-pass filter satisfies Formula 11. If we take the inverse Fourier transform of yj omega, we can get Formula 12. In this expression, Si is a sine integral function in mathematics. Let's take a look at its characteristic. The sinusoidal integration function is the integration of sampling function sine x over x. This is its functional characteristic. Obviously, the sine integral function is an odd function. Its maximum value appears at pi. Its minimum value appears at minus pi. According to the previous analysis, let's look at the step response waveform of the ideal low-pass filter. This is the input signal epsilon t. Its output changes according to the law of Formula 12. This is its output waveform. Obviously, there is also significant distortion between the input and output. Let's analyze the corresponding performance of its step response. This is its output waveform. In this waveform, the maximum value is at Td plus pi over omega c. The minimum value is at Td minus pi over omega c. Of course, here Td is the delay time of the system. From this waveform, we can find that it takes a while from its minimum value to its maximum value. This duration is denoted by Tr. It is referred to as rise time. Tr is equal to 2 pi over omega c, which can also be denoted by 1 over b. What is b? B is the bandwidth of the filter that converts the corner frequency to frequency. It is also the cutoff frequency of the filter, but its unit is hertz. Obviously, the rise time Tr of the step response is related to the cutoff frequency of the network, and they are inversely proportional. Let's look at the rectangular impulse response of an ideal low-pass filter. The analysis process and its step response are completely similar. I only give you its specific result. This is its input signal. It is a rectangular pulse. The width of this pulse is tau, and its output y1t is denoted by Formula 3. This is the time domain waveform of the rectangular pulse response. Obviously, there is also distortion between its input and output. Let's analyze its performance. Actually, when 1 over 2 Tr is much smaller than its pulse width, we can get such a waveform of rectangular impulse response. If tau is too narrow, omega c is too small, the rise time and fall time of the response waveform will be linked together. It may completely lose the pulse shape of the input signal. Next, I will introduce a new concept to you, Gibbs phenomenon. At jump point, or discontinuity in time domain, there is a 9% overshoot. Changing omega c has no effect on this jump point. The same is true for the previous step response. Here, changing omega c cannot change the height of this 9% overshoot. Therefore, in actual engineering, only if the rectangular pulse changes to another window function. Because the rectangular pulse is a gate function, it is also called a window function. So, only if the rectangular pulse is changed to other window function can this overshoot be eliminated. The detailed content will be explained in the course of digital signal processing. Finally, I will introduce an achievable low-pass filter. The ideal low-pass filter is not physically achievable. Figure 6 shows an achievable low-pass filter. This is an RLC circuit you have learned before. When the resistance R in the circuit is equal to root L over C, and if we make omega c equal to 1 over root LC, the system function Hj omega of this RLC circuit can be expressed by formula 14. Its spectrum characteristic is shown in figure 7. Figure A shows its amplitude frequency characteristic. Figure B shows the phase frequency characteristic. In its amplitude frequency characteristic, we can find that in the frequency range from minus omega c to omega c, it is approximate to the ideal low-pass filter. Its phase frequency characteristic from minus omega c to omega c is also approximately linear, especially in the vicinity where omega equals 0. It's basically linear. Formula 15 expresses the low-pass filter Ht. Its waveform is shown in figure 8. Here we can find that when omega c approaches infinity, Ht approaches delta t. We have mentioned the physical achievability of system. But what is condition for an achievable system in physics? In terms of time domain characteristic, the impulse response of a physically achievable system must be 0 when t is less than 0. In other words, a physically achievable system must be a causal system. In terms of frequency domain characteristic, Paley and Wiener proved that the physically achievable amplitude frequency characteristic must satisfy Formula 16 and Formula 17, which is called Paley-Wiener criterion. This is a necessary condition for the physically achievable system. From this criterion, we can find that the amplitude frequency characteristic of the physically achievable system can be 0 at some isolated frequency points, but it cannot be 0 in a certain limited frequency band. Therefore, ideal low-pass, ideal high-pass, ideal band-pass, and ideal band-stop filters are physically unachievable. As for this content, you can refer to the 4th edition of the book Signals and Systems by Jianjun Li. In this lecture, we mainly learned the frequency characteristics of ideal low-pass filter and analyze the time domain characteristic and the frequency domain characteristic of its impulse response, step response, and rectangular impulse response. And we know that the ideal low-pass filter is a non-causal system that is physically unachievable. By analyzing the performance of ideal low-pass filter, we can have a deep understanding of the characteristic of achievable low-pass filter. So much for today. Thanks for your attention. Goodbye.